In this video, we wish to introduce many of the main concepts and ideas of the subject area of curves and surfaces. To begin with, we are going to discuss the idea of a curve. Intuitively, what do you think a curve is? Maybe a one-dimensional geometric object. Or maybe a generalisation of a line. Perhaps the trace left by a moving point? Shown here are some examples of curves and some non-examples. Can you tell which are curves? By the end of this video, you should have a clear idea on the basic concepts of this subject.
In differential geometry, we're not interested in all types of curves, but instead particularly nice curves. What does nice mean here exactly? The tangent of a curve is absolutely pivotal to our study of it, so we'd certainly like the tangents of our curve to exist. Take a look at this curve. In particular, look at that nasty cusp that it has. Since the tangent of a parameterized curve is given by the derivative of parameterization, this curve simply doesn't have a defined tangent at t is equal to 0. We're not interested in these curves. Let's require that our curves are differentiable. Better yet, let's require that they are smooth, that is, all derivatives exist. We call these smooth curves. How about this curve? It's clearly smooth from the parameterization, but there's still a cusp. The culprit is a zero tangent. A point tracing out this curve would slow down to a stop and accelerate in a new direction. Let's further require that the tangent of our curve is never zero. We call such curves regular.
The subject of differential geometry borrows techniques and knowledge from many other areas of mathematics, namely linear algebra, Euclidean geometry, and integral and differential calculus, and some of the heaviest hitters of mathematics. This did not happen overnight, however. It began, as always, with the ancient Greeks and with the age-old questions. How much does a curve, curve? And how can we measure it? What is the curvature of a piece of contorted cloth, and what contraption do I use to measure this curvature? Such questions could not have been as rigorously answered by the Greeks as they would have liked. Approximations were the best they could do with the tools they had. What made matters more difficult was the development of more complicated geometries by René Descartes, as seen in the history of geometry, Cartesian geometry. Newton and Leibniz, the foundation layers of calculus, allowed finally for the curvature of a curve in a Euclidean plane to be defined as the rate of change of the tangents of the curve, and Euler defined the same thing for Euclidean space curves. It is important to note at this point, this was all done before the end of the 17th century, 2 centuries before the modern notion of a limit was defined. And so the solutions were not yet as rigorous as one might like. In fact, they are technically still approximations. The field was extensively developed by Gaspard Monge, and the modern definition of a limit, defined in 1817, firmly holding up to the intuition of the mathematicians previously named, Carl Friedrich Gauss in 1827 made an enormous breakthrough with defining what is now known as the Gaussian curvature of a surface.
Firstly, we wish to discuss the idea of plane curves. It may be apparent that in fact a plane curve is just a curve that lies in a single plane. Some examples of this include a line, parabola, ellipse, and a circle. It may be defined as so. When studying a curve, it may be useful to reparameterize by unit speed. Looking at the visualization, we can see that the rate at which the point traces the curve is non-constant. The idea behind unit speed reparameterization is that we aim to make this speed constant by finding the inverse of the arc length function and substituting this back into the original equation for the curve under a new domain. Unit speed reparameterization exists for all regular curves. This is useful as it simplifies many calculations. Also, we are able to define new features for a curve, such as the Frenet frame, which only exists if the curve is unit speed. The Frenet frame consists of 2 different features, the tangent and the normal. The tangent to a curve is a straight line which meets a given curve at one point. At this point, the gradient of the tangent is equal to that of the curve. As our curve has to be unit speed for the Frenet frame to exist, the tangent is a vector of length 1. Similarly, because of unit speed, the normal is given by the 90-degree rotation of the tangent vector. Therefore, the normal is also a vector of length 1. The visualization shows this moving frame, which can be used to describe a specific curve. Another important feature we need to observe when viewing a plane curve is the curvature. This is the degree to which a curve deviates from a straight line, or as we will see later, how a surface deviates from a plane. The curvature of a plane curve can be given as so. If a curve is unit speed, the curvature may be given by the simplified equation. Viewing these two circles intuitively, which has more curvature? Or maybe, do they have the same value of curvature? In fact, with a circle, the curvature is defined as the reciprocal of the radius, so the higher the value of the radius, the lower the value of the curvature. Therefore, the larger the circle, the less curvature it has. The curvature is very useful in describing a plane curve. However, a more descriptive notion is that of the sine curvature. This is defined for plane curves only. Not only does it describe the curvature, but it also describes in which direction the curve is curving, towards or away from the normal.
We would like for the notions that we developed while working with plane curves to also apply to space curves, that is, signed and unsigned curvature, the Frenet frame, and so on. The problem, however, is another spatial dimension. Consider two different curves of unit speed. Taking the norms of the rate of change of these tangents shows that alpha and beta of t, that is, their unsigned curvatures, are equal to 1. What we need is something more sophisticated, but it requires another definition before getting to that, due to there being no preferential direction of rotation of pi over 2, as there is another pesky spatial dimension to concern ourselves with. We must first redefine our definition of a normal vector, that is, a definition in which a vector that is normal to the tangent, that is in the plane of the tangent. What we need now is a vector that is linearly independent of the tangent and normal vectors and is a rotation of pi over 2. So we will define this vector as the binormal, which will be the cross product of the tangent and normal vectors. Finally, we can define the torsion as the following equation. The negative sign is simply a matter of convention, as the torsion measures the turnaround of the binormal vector counterclockwise. Our Frenet frame is now given by the following set, and by defining the binormal in terms of a unit speed curve, that is, found the tangent and normal of that unit speed curve, we have constructed a Frenet curve atop our map. If we are to consider the same space curves alpha and beta of t again, we can see that their torsions are given by the following. This aligns with our intuition that the curves are different and should weave differently to each other. So, with the following at hand, we can now consider some more complicated curves. Consider the following plane and space curves, for example. We find that the torsion of the space curve equals to 0, so a natural question is to ask, is the space curve some rotation of the plane curve? Are they really the same curves in disguise? Unfortunately, they are not, as they have different curvatures. Neither deviates outside of some plane. For the plane curve, it is impossible for it to do so by definition, and the space curve has 0 torsion and hence is planar.
Now, what intuitively do you think of as a surface? Perhaps some region of space with an area but no thickness? Maybe some sort of generalisation of a plane that isn't necessarily flat? If we loosely think of a curve as being parametrised with 1 degree of freedom, let us think of a surface as being parametrised with 2 degrees of freedom. As before, we're interested in particularly nice surfaces. Naturally, we'll require that the parametrization is smooth with a continuous inverse, and it's convenient that our surface does not self-intersect. Now, look at this cone. In particular, look at the sharp point at its apex. We like to be able to talk of the tangent space of the point of a surface, which we might think of as the plane that best approximates the surface at this point. No such plane exists at the apex of the cone. Let us exclude these types of objects, which we may think of as excluding objects with sharp points. Let's look at an example of a regular surface. This one is well known as Shirk's first surface. We are interested in the curvature of curves, and we're just as interested for surfaces. The Gauss map is a function that associates each point on the surface with a unit normal vector of the surface. The rate of change of the Gauss map can tell us a lot about how a surface is curving and by how much. We can also look at curves within surfaces. How about this curve? Does it look familiar? This is our space curve from earlier, and it lies completely within our surface. The normal curvature of a curve within a surface is the amount of the curve's curvature in the direction of the surface normal. Two curvatures, called principal curvatures, that arise from the rate of change of the Gauss map also arise in this setting as the largest and smallest normal curvatures of any curve on the surface. For this particular surface, the arithmetic mean of the principal curvatures, which is also known as the mean curvature, is 0. This makes our surface a minimal surface. This means that our surface locally minimises its area, and every point of the surface is a saddle point. It was Lagrange who first considered the problem of finding a surface of least area stretched across a given closed contour, though he did not succeed in finding a solution other than the plane. Physical models of minimal surfaces can be formed by dipping a fixed frame into soap solution.
Thank you very much for watching.